Volumes of revolution, the Wasser method, part 1. Let's look at a function f of x and consider the region beneath the graph but above the x-axis on the interval x equals a to x equals b. We want to take that region and revolve it 360 degrees about the x-axis and find the volume of the shape that it makes. Now, we have learned in calculus that when we want to find a measure, for us things like a length or an area or volume, we will start with a simple geometric shape, in this case a rectangle. We will revolve this 360 degrees about the x-axis, find the shape that it makes, and find its volume. My claim is that if I were to revolve this rectangle 360 degrees about the x-axis, it would make a circular disk. Well, the area of any circle is pi r squared, but this has a small width, delta x, so that will give the volume of that one cross-section revolved about the x-axis. If we want to approximate the total volume, we would draw many of these cross-sections, starting at x equals a and going to x equals b, revolving all of those about the x-axis, where each volume is pi r squared times delta x, and then adding all of those volumes together. Of course, to find the actual volume, we would simply shrink the width of our cross-section down to 0. That is, let delta x go to 0, or delta x goes to dx. And then add all of those small circular disks, starting at x equals a and going to x equals b, together. The only thing missing here is the radius. It's one of the reasons that I recommend drawing a cross-section, because I know that the length of the radius is always going to be big minus small. In fact, the length of anything is always going to be big minus small, where the big y value is f of x, and the small y value is y equals 0. Let's take a look at a specific example. So let's consider the graph y equals f of x. Equals the square root of x. And let's look at the region from x equals 0 to x equals 4. We want to revolve this region 360 degrees about the x-axis. So I'm going to start by drawing a representative cross-section, a rectangle, and revolving that about the x-axis, knowing that I'm going to form a circular disk whose volume is pi r squared times dx. Now, I drew it big so I could see it, but you have to assume that the width is actually infinitesimally small. And then we're going to add all of these tiny volumes together, starting at x equals 0 and going to x equals 4. This would give me the integral 0 to 4 of pi times, well, I'm missing my radius. Well, what is the radius? Well, the radius, as we drew it, is the big value, big Y, root x, minus the little y value, or the smaller y value, 0. So plugging it in, I get the volume is the integral from 0 to 4 of pi times r squared dx. Since r is the square root of x, r squared is x. Now we can find the antiderivative. I will do the constant rule, then the power rule on the interval 0 to 4. I like to factor the constant out almost always. And then we're going to plug in the upper limit, 4 squared over 2, minus, plug in the lower limit, 0, which says that if I were to take the region bounded above by y equals root x, below by the x-axis, on the interval x equals 0 to x equals 4, and revolve that region 360 degrees about the x-axis, the volume of the shape that it makes would be 8 pi.